So now what I'm going to do is I'm going to go to our slides, and I'm pretty sure I remembered where we were. We were talking a bit about measurement, and I know it's probably long in your past, and it's hard to keep track of the things we talked about with regard to measurement. I talked a little bit about error and the fact that all measurements have error, and this is with regard to the fact that in the operation of the so-called scientific method, what we operate under as scientists, ultimately we look at what goes on and we try to figure out what's going on. And as part of trying to figure out what's going on, we have to design processes to test what we think, and the hypothesis we assume that the process is operating under. And so this requires measurement. It requires measurement in the process of testing what we think is happening, and oftentimes it requires measurement when we're making the observation of what goes on as well. And we have very specific rules about making measurements, and we talked about several of them as we've been going along here. And I want to just do a little bit of conclusion with measurement and using measuring devices, because I want you to think a little bit about them. And I'm going to have a couple questions on our practice, our little Moodle module that we will answer with regard to how to do measurement. So we're going to say just a few things about the style, the approach that you should take when you make a measurement with a measurement device. Because again, the premise behind this is the fact that everything you measure has error. We can never get the right answer. And there's a couple reasons why we can't get the right answer. The first being that maybe the device is not measuring correctly, or maybe you don't know how to use the device. Now let's assume we eliminate those possibilities. Now that's always a little tricky to make sure that you have eliminated them, but we will assume we have eliminated what we call the systematic error due to lack of ability to use the equipment or faulty equipment. So we eliminate that. It still boils down to the fact that measurements are real numbers. Real numbers are infinitely significant, meaning they have an infinite number of decimal places, and absolutely no measuring device we can possibly use can measure something exactly, because you just have a limited measurement. And as I talked a little bit about at the very last time we were together, essentially what you can use as a rule of thumb is that for every digit you wish to get towards the accuracy of a measurement, spend 10 times more dollars to get the next digit. And that's pretty incredible when you recognize the fact that there are numbers that we know in science that are known to 9 digits of accuracy, 8 digits of accuracy. It just tells you the kind of money that was probably invested to get those numbers to that degree of accuracy. And believe me, that kind of money was invested, because it's very important to know some of these numbers very accurately, particularly like when you're talking about heading out into space and you're aiming for Mars. Well, Mars is upwards of 90 million miles away from here. And if you make a slight trajectory error, just a slight one, by the time you've gone 90 million miles, you have made an incredible propagation of that error into your position you will end up at. So it's very important, particularly on the large scale and on the very small scale, which we very commonly deal with. And as we move forward, we're going to be talking more about matter and its interactions. And of course, matter is very small scale stuff. So it's very important that we are able to make measurements of these very tiny numbers when we're doing such things, with lots of decimal places required during those measurements. Okay, so what I'm going to do, I believe, is I'm going to try now to put some slides up. We're going to talk a little bit about the tricks I want you to think about when you make a measurement and when you're reporting a measurement, and just how carefully you can actually make a measurement from a device. Now, naturally, if the device is electronic, and more devices are electronic, you can only report or use the digits that are displayed to you. So there's really no issue. You just look at the device, it spits out numbers, and then the numbers that it spits out, you would report. But you now must think in terms of what we're talking about with regard to error. There's a mistake in this number. It's not completely perfect. Now we're again going to assume we've gotten rid of any systematic problem, meaning the device is working, and I know how to turn it on and get the number off of it, so we got all that part straightened out. There is still inherent error based on the fact that the last digit that it shows had to either be rounded up because it was really a little less than that, or truncated off, so really it should be a little more than that when you just lopped it off to the last digit. Okay, so we call this a random error because we're going to assume, statistically speaking, half the time that last digit represents a lopping off, so that there's a truncation, and half the time we move the value up and round it up to put that last number, so it's a little bigger than it should be. So the randomness is reflected in, statistical speaking, half the time up, half the time down. Okay, so let's then show, what do I do if I have a ruler? What rule of thumb should I follow to properly put the correct significance onto that value? So I'm going to present my screen for a moment. And what does this say? I should probably allow the window or screens to share. I don't know what I'm doing, so I'm going to hit this. Oh, I got to choose. Select window. Oh, which one? Oh, lecture 1. That's the one I want. Okay. Aha, I got there. Hey, I almost did that myself. I only got a little prompting from the studio audience, a little bit. Getting a little better here. So I'm going to go with my slideshow from the current position. Okay. So if you have normal lab devices like beakers and rulers and mercury thermometers that you, in the good old days, you would read the expansion of a liquid off of, and you're attempting to properly report the number, what you do is you look at what we call the calibration on the scale. You look at what place it's ruled to. Then the idea is you estimate one more digit, and that's it. That's it. You don't make any additional estimation beyond one digit. So that is going to be the digit of error, the one that you're guessing what it is. And then you assume that this random error or this unknown error is present in that last position. I think I'm going to take these off because you know what happens? I start spitting steam up into my glasses and I can't see what I'm doing too well. Okay, so very simply, let's look at how we would follow this procedure on something calibrated like such. So this is something obviously holding a volume of water, and there's a so-called interface between the air and the liquid, and we call that interface a meniscus. Meniscus is the point where the two different phases of the material meet, and of course that's where we're going to be measuring our volume of water relative to that. So here's the very simple procedure I want you to note, and we can summarize it in one sentence by saying this is ruled every 10 milliliters, and we can see that, 10, 20, 30, 40. And typically, decades of ruling are our favorite. We like it in chunks of 10. Why? Because now what I'm going to do is guesstimate one place past the tens. So if this is ruled to the tens of milliliters, I can therefore guess to the ones, and that's it. So if you were going to report this, I'm saying it, okay, in actuality, you should take this meniscus and read from the bottom of it, and it's usually like a curved surface. The meniscus is usually a curvature, and the curvature comes about because the liquid in the container is attracted to the glass in the sides, and it kind of crawls up the sides a little bit. That's a very important process, and we're going to talk more about that later in the semester. the attraction that molecules exert on one another. So these molecules then are what we would call polar molecules. There's the water in the container is polar. The glass, believe it or not, is polar, meaning it has little individual separated entities of positive and negative charge. And these opposite charges attract one another. So the water molecules near the edge of the container literally get yanked up to the sides of the container. This is called capillary action, and it's also called wicking sometimes, because the same thing happens in a candle as the wax melts. It moves by capillary action due to the polarity of the materials through the wick, and it climbs up into it. This is the same thing that happens in a tree. I mean, believe me, there are leaves in that tree that are sometimes 100 feet or even more above the ground. And how do you think the water gets up into those leaves? There's not a pump at the bottom of the tree that the tree is operating to send the water up to that leaf. It literally is climbing through the polarity of the cellulose in the wood, and the polar water molecules with their little plus and minuses are literally just pulled upward by the polarity of the chunks of wood, the cellulose in the wood, and eventually the polarity is such that it pulls the water all the way to the top of the tree. So this is how a paper towel works too. You dip the paper towel into the water, it sucks the water up into it via this so-called capillary action. Okay, so in any event, we have this typically curved surface that the water and air interface possesses. Typically what you should do is try to measure from the bottom of it, more so to be consistent than anything else. So you measure from the bottom of it, and I'm going to say it's about halfway. Now you might say it's a little more than halfway, but that's okay. Why? Because there's air, and it is understood to a person that understands the connotation of measurement that this last digit I'm going to show you ain't exactly right. So there's some air in this last digit, and I'm going to report 16. Now, so I'm saying it's a little more than halfway. And again, you might have said 17. Some of us might have said 15. But statistically speaking, now we would build that curve I talked about. We would build a bell-shaped curve of all the answers, and we would pile up how many people said 16, how many people said 17, how many people said 15. And if it's done over statistically a whole bunch of people, we'll get a nice Gaussian or normal bell-shaped distribution of all the measurements around that value. Now, if there is random error present in the last digit of maybe plus, or if I get a tolerance from the manufacturer, maybe it's plus or minus 1 unit of error in the last digit, then probably the real answer is somewhere between 15 and 17. And I could certainly believe that for a measuring device like this. Okay, so when I post our little module for you to do, here's all I'm going to be asking you to do. I will give you various devices with various things to measure from them, pictures of them. You look at what they're ruled and you give me one more digit, and that's the deal. So just give me a digit past what you know for certain, and that's because that's where the error begins. Do not give me any more digits, because you're implying extra accuracy beyond what you can see on the device. So for instance, here I have a nice little ruler. We would call it a meter stick more technically. It's ruled in centimeters, and actually you should note it's ruled in tenths of a centimeter. 2.1, 2.2, all the way to 2.9, and then 3. So this is ruled every tenth of a centimeter. And so the simple answer is report 1 place past the tenths. Then you're done, you're golden. And the digit you're going to report to will be where the error is. And it's okay. It's really, truly okay for you to pick a number that doesn't coincide to my number, because if you understand error, we know that that's where the error is. So this is, I see 2.5, 2.6. I'm between 2.7 and 2.8. We know that for sure. I mean, it's kind of hard to say. Again, it's about halfway. Okay, so I'm going to say, I said 2.74 on this answer. And probably if we polled the room, we'd probably get more 2.75s than we get 2.74s. And of course, I'm going on the fact that I'm splitting the graduation between 2.7 and 2.8 in half, and half of that would be 0.05 more past the 7 to the 8. So again, this is why we kind of like a decimal scale. Decimal scales give you this ability. Now, what wouldn't give me this ability? An inch scale. Now, think about if you look at your traditional ruler that you used your entire life probably when you made measurements in grade school and junior high or whatever. It might be ruled every inch, but it's probably got little marks. It's probably got ½ inch, quarter inch, and maybe even 1/8 or 1/16 of an inch. That's great. So it has lots of graduations. So you could get down to the 1/16 of an inch. But when you're between the 1/16ths, what are you going to do? Can you tell the 30 seconds? No. You need a scale based on powers of 10 to give you that last digit so that you can estimate somewhere between 0 and 9 for that last digit instead of trying to do how many 30 seconds that is from the 16th mark of this to the 3/16 to the 4/16. That gets really tricky. So really scientists prefer this calibrated in units of 10 scales. And I think that is familiar to all of us what the calibrated in unit of 10 scale is, but I'm going to save the answer to that for a slide that we're going to show here in about a couple minutes. Okay, so just a couple more examples. Oh, by the way, if this has a tolerance, and so you get the ruler box out, and the box says tolerance of this ruler is plus or minus 0.03 centimeters. I'm reporting 2.74. The world would say the curve is going so that the bottom of the curve is probably at 2.71 up to a maximum around 2.74 and then tails back down to the very few people will be reporting at 2.77. So that's the range of, if you like, confidence that we would have in that measurement using that measuring device. Okay, so one more time, when you go to Moodle, and I have pictures like this, look at what it's ruled to, give me one more. I really don't care so much what that one more digit you give me is. I'm just more concerned that you give it to me into the right number of digits. That's the concern. Okay, so here we have something like this. Now, again, this comes to the tricky point of the so-called meniscus of curvature. And again, if you're looking at the back side of it, which I'm calling the part that's above the 3 milliliter tick, or if you're looking at the front side of it, which I'm saying is below the 3 milliliter tick. Okay, now first of all, maybe let's get clear here. This is ruled every 1 milliliter. It's certainly more than 60. It's more than 61. It's more than 62. I'm claiming it's between 62 and 63. Again, I'm going to go from the bottom of the meniscus, so I'm going to claim it's between 62 and 63. I'm going to claim, again, it's maybe 8/10 of the way up to the 3 from the 2. So there's my idea of the meniscus. It's the air-liquid interface. And I read from the bottom of the meniscus, and I'm going to claim 62.8. Now, if I look at the manufacturer's supplied guess rate, and because of the fuzziness of the meniscus, this quite frequently would be something like a ½ mil error in it. So if we now did this with thousands of people, the answers would form a bell-shaped curve probably between 62.3 and 63.3, probably strongly peaked at around 62.8, probably. Okay, again, now let's notice the difference here. Just like the one on the left, the one on the right is ruled every 1 milliliter. But the difference in the one on the right compared to the one on the left is the spacing between the 1 milliliter marks. There's more room between the 1 milliliter marks on the measuring device on the right compared to the room between the 1 milliliter marks on the device on the left. Now, what this ultimately allows for is for you to be a little more discerning. You can look a little more carefully, and you can much more accurately judge the height or difference between 1 milliliter, the fraction of a milliliter in the one on the right compared to how much of a fraction of a milliliter you are wrong in the one on the right, on the left, excuse me. So because of the spacing of the marks, you can get more accuracy in the measurement. Now there's two ways to get more spacing. Well, there's actually only one. You make them skinnier and taller. If you make them skinnier and taller, then you can get more spacing between the so-called graduations. You'll notice that what I'm saying here is the cylinder on the right has a 0.1 milliliter tolerance compared to the cylinder on the left that has a 0.5 milliliter tolerance. You're going to get more error in measuring when the clicks are spaced closer together than you will when the clicks are spaced further apart. So again, I'm going to say I'm a little more than half. I guess, I said half. I'd probably most of you would say 8.6, but again, that's what we would say maybe is within the error region of this, but it's ruled to the 1, guessed to the tenths, and that's the bottom line. Okay, now then just a couple more examples. This is a scale that is ruled every 1/10 of a gram, which means you report to the hundredths of a gram. I'm beyond 17.1, 0.2, 0.3, 0.4. It's a little more than 17.4. So I guess between 0.4 and 0.5, how many hundredths of the way I am, and I'm going to just divide up into chunks of 10 values. And I'm going to claim here 17.42. And again, if you read the tolerance and found 0.04, then I would assume it's somewhere, the bell-shaped curve of all measurements would be as shown. Okay, now one last one I want to show. This is for the cookie. If we get this one right, I'll bring cookies. Not for the people online, just for the people in class. That's the benefit of coming to class. Why? Because this shows that we get the idea here entirely. You might say that's right on the 3, smack dab 3. I should report 3, but you have to also include how certain you are that that is 3 based on the significance of the measuring device. According to what we have discussed, this should be reported to the hundredths position. It's known to the tenths, you're guessing in the hundredths. And people who see that number understand the error is present in that hundredth digit. So I will report this as 3.00, the last digit showing the error. If you move it a smidgen to the left, it'd be 2.99 you would report. If you moved it a smidgen to the right, it'd be 3.01 that you would report. Okay, so again, in conclusion, eventually I will send out an email announcement. You can go in there and click on the pictures, answer the pictures, make me happy, get your points. Okay, now let's talk about this idea I already mentioned to the fact that in certain unit scales, it's a little more difficult to do this game I just discussed. Now, why is that? Well, first of all, we should probably mention where most unit scales were developed, what most unit scales were developed for. It's pretty obvious, I believe. Science wasn't really around as long as humans undergoing commerce. So most unit scales were designed for commerce. And with that in mind, they used convenient scales to make measurements. And over time, a set of commercial units evolved. Like what? I mean, we can name them, like a bushel and like a ream, and just on and on and on it goes. There's just a dozen, and on it goes. There's just a myriad of measurement units that, again, were designed not to speak and converse scientifically amongst each other, but were designed to help us trade and barter and whatever we would like to do. Now, of course, this had to include the kind of units we're discussing, like mass, how much things weigh, like length, things of that sort. But again, they were chosen for reasons of convenience. Like, for instance, you measured the height of a horse in hands. So if you take your hand like this and go to the ground and move up like this, and a horse was so many hands tall. And then the King of England decided he would introduce the foot, and it was based on the length of a foot, of his foot. Well, technically it was anybody's foot. You could just use your foot, and that would be a foot of length. And of course, then you could measure feet in that regard. But here's the real issue that boils down from this system of units when we get to start to try to think scientifically, trying to be really accurate with what we're doing. What we now would call a system of units like that, we would call it irrational. This is an irrational system of units that we typically use in our units of commerce. Now, when I call it an irrational unit system, I don't call it that because it's insane, but we call it irrational because what happens numerically when you apply it. Now, here's what I mean. Numerically speaking, let's just go with length. We all know an inch. An inch is about, a chunk of space, kind of like this. And then we'll go to the next most common unit of measurement, and that's the foot. And we all know there's 12 inches in a foot. But what I'm claiming is there's an irrational conversion between inches and foot, because not all for all numbers, but when you divide by 12, changing, if I have 17 inches, and then I divide 17 inches by 12, I've changed a rational number into an irrational number. My calculator will spit out all these decimals. So I'm using an irrational unit system because how it changes a finite number into an infinite number. Now it even gets crazier. If I change my feet into miles, there's 5,280 feet in a mile. So I take my distance in feet, divide by 5,280, and once again, I'm whacking the number out into a very crazy system of scaling. So these units that were designed for commerce, it turns out were not really good. I mean, it's not that we didn't use them for a long time, but they weren't really good for use in science because of when you start manipulating the numbers and converting the numbers, crazy things happen to the numbers. And it made it very inconvenient for using those kind of systems. So what a bunch of old white guys like me did was they got together and the old white guys decided these are the units we're going to use. And it was called the System International. So the System International was the chosen units by International Congress that when you converse in science, these are the units you got to use. So what I'm going to list here is a short list of these so-called units, and it's short because this is the list. Okay, so in formal communication, when scientists speak science to each other, we are speaking the same language, and that language includes using the same units. So we're all going to speak in the same units when we do so, and those units are the SI units. These are the SI units. Now, first of all, I will point out that these are all in rational scales as well. Now, what do I mean by them being in rational scales is that they're in decimal scale. So when I change, once again, there are various lengths in this rational scale. I don't have to use meter. Well, let's be a little careful with that. When I make subdivisions of the standard unit, I don't change to inches or furlongs or rods or something like that. I change to centimeters or kilometers or nanometers or micrometers, all based on the meter. How do they differ from the meter? In powers of 10. So a centimeter differs from a meter because there's 100 centimeters in a meter. A kilometer differs from a meter because there's 1,000 meters in a kilometer. A megameter differs from a meter. There's a million meters in a megameter. So in the metric scale, it's rational. What do I mean by that? When you change between metric units, you don't divide by crazy numbers. You divide by 10 or multiply by 10. Now, you might divide by 1,000, you might divide by 1,000,000, but all we do, and I think we can think about it, you slide the decimal point. The number never changes. Whatever number it is in meters, it's the same set of numbers in millimeters, it's the same set of numbers in nanometers. So that is convenient. That is what we would call rational in terms of not crazy, but in terms of being so that you're not changing a fixed number into an infinite number. So we use a rational unit scale when we're doing these things. So when we measure length, we use the meter. Now, what is a meter? A meter is a little more than a yard. A yard is 36 inches. A meter is 39.4 inches or so. So it's about almost 3.5 inches more than a yard. Now, why? I honestly can't give you solid rationale as to why it's different and why it's more. I don't know. All I know that it is, okay? And for mass, instead of using pounds, we use kilograms. Now, I also know that there are 2.2 pounds in a kilogram. So if you have 10 kilogram mass, it's 22 pounds of mass, for instance. And again, why it's different and for what reason, I don't know, but it is. So when you weigh masses out, you should use kilograms. Now, time is familiar to us, but technically we're supposed to use seconds. Now, I will say this, that's not really a rational scale. We all know that, right? Because in seconds, if I want to convert seconds to hours, I'm not dividing by a power of 10. I'm dividing by 3,600. Let's maybe go a little easier here. If I'm going to go from seconds to minutes, of course, I would divide by 60. There's 60 seconds in a minute. If I'm going from minutes to hours, of course, we know there's 60 minutes in an hour. So again, these are getting into these irrational scales. And if I'm going to go from hours to days, I would go divide my hours by 24. That's an irrational time system. So how do scientists get around that problem? We don't use hours. We don't use minutes. We don't use days. What do we use? Milliseconds, nanoseconds, kiloseconds, gigaseconds. We put the second unit onto the metric scale, and we use the same metric prefixes that you would use to move the length to smaller and bigger chunks, to move time to smaller and bigger chunks. So that's how we make time into a rational scale. We move it into metric time, as weird as that might sound. Now, of course, it's not as if I don't talk about it in my lab. You know, this experiment's been running for an hour. I would say that, yes, but I really should be a little more careful, because that's 3.6 kiloseconds is what I should report when I'm using the approved unit system. But we just do things like that. Okay, now let's talk about temperature. And we're going to say more about temperature later. Temperature is a very interesting property because it's kind of weird. It's really, what is temperature? When you come right down to it, it's a sensation. I guess the easiest thing to think of what temperature is I would think of it as a feeling I get. I certainly know when I'm hot, and I certainly know when I'm cold. But just really, what does it ultimately mean? Well, what it really means is it's a measurement of the energy bath you're subjected to. There's a certain amount of energy in the form of heat available to us that slams into us, and if we're in a cold environment, we might be transferring heat out. If we're in a hot environment, we're getting heat transferred in. Heat is always being transferred unless you're in so-called thermal equilibrium, unless you happen to be at exactly the same temperature as your surroundings. If you are, then it's giving you heat and you're giving it heat, but you're exchanging heat equally. If you are in a colder environment than that the cold environment is really technically not cooling you off. Technically, what's happening is you are heating up the colder environment and you are losing your own heat energy in the process of delivering the heat to it. So you're not really technically being cooled off, but you are heating up your surroundings in a case like that. Now, heat is energy, and we will get into more of these ideas in much more detail later, but how do we sense heat energy? I think your mom and them know the answer to that. We put a thermometer in there. So the thermometer is a sensing device that tells us about the ambient energy that we're subjected to. So therefore, we need a scale to measure temperature. And we choose this very bizarre scale, which maybe some of us in here have never heard of. It ain't Fahrenheit. It ain't even Celsius. It's something called Kelvin. Well, before we delve into it any more than that, just let me say a few words about the more familiar temperature scale, because they have cool stories. Everything really has a cool story. And believe me, I could spend a lot more time on every little detail of everything I talk about. Why? Because this is my life, and I got not much else going on in my life. And so you guys are like captive audience, and you kind of have to listen to me, except all the people out there who have muted me by now. Everybody in here is forced to kind of listen to me, probably intermittently, but still forced to listen to me. So let me tell you a little story about the various temperature scales that you probably have heard of. First of all, of course, there's Fahrenheit. Fahrenheit is named after Daniel Fahrenheit. And Daniel Fahrenheit is the guy who invented the thermometer. And of course, there was a need in the 1700s to be able to sense energy. And what was noted was that the magic material known as mercury had all kinds of weird and crazy properties. And one of them was that when you warmed it or cooled it, it expanded and contracted incredibly, really far. So if you put mercury onto something that was hot, it expanded like crazy. If you put mercury onto something like that was cold, it contracted like crazy. And so it took up way less space when it was cold, took up way more space when it was hot. Well, this led Fahrenheit to say, well, wow, I can use this to scale energy by marking it off in what we'll call degrees. Now that's an interesting point in itself. We call it degrees of temperature, and your mom and them know that. It's so many degrees out. So what's the deal with degrees? Where did the idea of degrees come from? Well, the idea of degrees comes from what I will call relative measurement. And what is a relative measurement? Well, let's go away from temperature for a second and circumnavigate the Earth. And now what I can think of is a moment at the equator, and I go 10 degrees north latitude. And of course, what that means is I'm making an angle between the equator and me that is equal to 10 degrees. Now, this is really the same thing that you're doing on your thermometer. Fahrenheit decided that 0 degrees Fahrenheit was the coldest thing he could make. And in the mid-1700s, what was the coldest thing he could make? It was a mixture of salt, water, and ice. And believe it or not, that was as cold as it got. They couldn't think of any way to make anything colder. First of all, I'm sure we all know that when you put ice in water, it's cold. But actually, if you add salt into the ice with the water, it gets even colder. And what Fahrenheit did was he saturated or put as much salt as he could into water, dumped ice into it, stirred it all together, stuck his pile of mercury in a tube in it, and it shrunk. And it shrunk as far as it would, and he marked it off and called that 0 degrees, or 0. He just called it 0. The coldest thing he could make was 0. Now, if he had pure water with ice, not salt water, does anyone want to guess what the thermometer would rise to? Let's think. What do you think? Anybody want to offer a guess? Okay, so you've mixed, I told you, it gets as cold as possible, Salt, water, and ice all mixed together so that the ice doesn't melt. There's still ice and water and salt in there, and he called that zero. Now, if he did it with pure water and the ice isn't melted, put the same thing in, guess what? The mercury expands. Where do we think it stops, and what temperature would it stop? Let's say, what does water and ice, where does 32 degrees? 32 degrees, that's where water freezes. So when ice is allowed to exist, the water has to be at 32. So when his salt water saturated solution could get colder, the liquid would expand less, and it was at zero. Now, when he put pure water, it came up to this point that he just divided it up into equal chunks and called it 32. Now, here's why he called it degrees. Because it's the same kind of deal. I'm at zero. I've now made an angle of if I measure the angle from zero that my mercury went up, I'm going to measure that in an angle of 32 degrees. And then he put it in his body orifice. I'm not sure which one. And first, I'm not sure what the reasoning behind it was. He decided that would be 98. So he put it under his armpit or whatever and let it expand, marked it off, and called that 98. So he, again, could say that in the saturated salt water, it's as small of a column as it would get. Now it will expand upward, and I can measure that in degrees of change. And so that's why temperature is called measured in degrees. Now, a guy by the name of Celsius didn't like that, using the saturated salt water, because a lot of people couldn't do that and make their scale, and body temperature, because a lot of people had different body temperatures. So he just said, why don't we just use pure water and boiling pure water? And I'm going to call pure water 0, and I'm going to call boiling pure water 100. And so many people decided to call that centigrade, because there's 100 units between freezing pure water in the centigrade scale, Celsius scale, and up to 100 degrees for the boiling point of pure water. On the Fahrenheit scale, pure water boils, and maybe some of us know, maybe don't, 212 degrees Fahrenheit is the temperature at which pure water boils on the Fahrenheit scale. So that's where the difference in the scales comes from, based on the starting points where they're designed. Essentially, the important one is Fahrenheit scale is for saturated salt water with ice. Celsius scale is for pure water with ice. To start at 0 Celsius, pure water and ice. Fahrenheit, start at 0 Fahrenheit, salt water and ice. Now, if you're going to ask me, then why didn't one of them just win and the other one lose? Really, one of them did win. Celsius won. Everybody uses Celsius. And when I say everybody, I mean everybody. I don't just mean Europeans. Every country on Earth except 2, and I can't even think of the other country. There's only 2 countries on Earth that use Fahrenheit, and of course we're one of them. Everybody else uses Celsius. Everybody. I don't. As a matter of fact, everybody else uses metric system, the divide by powers of 10. Nobody uses inches and feet and miles. Nobody on the whole planet, except the good old US of A. We stick with our metric or with our English, our old imperial unit systems, because we're a little bit stubborn. When I was a kid, your age, there was a big push in the early 70s to convert to metric. And they changed all the road signs to kilometers per hour and all this stuff. And they started changing the road signs to how many kilometers it was to the next town. And people just revolted and just got so PO'd about it that they said, all right, we give up. We're not going to do it. But of course, I think we're all aware, when you buy Coke anymore, you don't buy You don't buy it in quart. You don't buy it in a pint. You buy it by the milliliter. You buy it in a 2-liter bottle. I mean, so it's eventually winning. We're winning over to the metric system eventually. Like, what's a handle? What's that? Come on, any frat boys here? Handle of, is that 1.75 liters?
No frat boys, sorry.
1.75 liters in a handle, the good stuff. We used to buy by the fifth, which wasn't even a quart. It was a fifth. 4/5 of a quart was called a fifth. And when I was a kid, we always bought fifths. But slowly but surely, the metric system is creeping in. I don't think our Fahrenheit system will ever go away. And I'll tell you why I think the Fahrenheit system is so enamored in America. It's because it fits the temperature of the climate beautifully. And what I mean by that is, as cold as it gets in this country, take the whole country and encompass it, it doesn't get any colder in this country than 0 degrees F. It doesn't get any hotter in this country than 100 degrees F. So the Fahrenheit scale fits the climate of the country beautifully. And, well, generally speaking, where people live, it's between 0 and 100. That's what I would say. And so since it's between 0 and 100 where people live, we like to deal with numbers between 0 and 100. They're easy to write down. I think I mentioned this before. That's why football uses this archaic measurement of length of yards. The only reason it uses yards is it fits the game perfectly. All the statistics, the play of the game, it's 0 to 100. And everything fits on that nice scale. So I would make the same claim with Fahrenheit. We love Fahrenheit because most of us don't think scientifically. Most of us really like to brag or complain about the weather. That's what we like to do. So we're going to stick with the Fahrenheit scale. Now, the weirdness is that I'm not even going to use either Fahrenheit or Celsius. It's long blathering I've just been doing. The temperature you're supposed to use is something called Kelvin. And what is Kelvin? Well, this was designed by crazy scientists that didn't like the fact that 0 on either of these scales was not as cold as possible. Now, it was as cold as possible in 1700, but as time progressed, we realized that we could make things way colder than 0 degrees Fahrenheit or 0 degrees Celsius. Way colder. As a matter of fact, what you do in Celsius or Fahrenheit is you use negative. Minus 20 below 0 and all that craziness is what you will say if you're in Alaska. Well, they didn't want negative temperature because that's an indication that there's negative energy. They always want to count energy in positive units. So what the Kelvin scale is designed to do is use the coldest possible temperature and call it 0. And then you have to start thinking about the theory of what is temperature. Temperature is measuring motion. And the hotter the temperature is, if we had little nanoscopes and we could see everything in this room, and I made this room hotter and hotter and hotter, the air in this room would just move crazier and crazier and crazier. That's all that it means. The hotter the room, the crazier the air is moving. And as a matter of fact, that's all it means when you put the turkey in the oven. Put the turkey in the oven and you turn on the burners or the coils. What the coils do is they put energy in, of course, but they put energy not directly into the turkey. They put energy into the air in the chamber. And the air in the chamber is now running around like crazy. And if you reach in there, you go, whoa, that's hot. I better get my hand out of there because my instinct is if I leave my hand in there, it's going to look like the turkey in a few minutes. So I instinctively get my hand out of there because I sense the heat. And ultimately, what does that mean? The sensation of heat is due to the fact that the molecules in the chamber are running in there like car. If I had nanoscopes, I'd be like, wow, look at them go. They're going like crazy in there. They slam into the turkey. They impart momentum into the turkey, and it invokes a chemical change in the matter of the turkey. It changes the composition of the turkey matter by imparting energy into it. So this is when we knew and understood more about what temperature was measuring. It was measuring energy. They said, why stop at 0 to begin the temperature scale? There's plenty of energy left at 0 degrees Fahrenheit or 0 degrees Celsius. Let's just keep shoveling the energy out and letting the temperature continue to go down. But we don't want to call them negative values as we do on the Fahrenheit or Celsius scales. I still want them to be on a positive sense. I want to start my temperature scale, or I'm sorry, start it when I've removed all energy. And what that was called was absolute 0. If you get to absolute 0, there's no energy left in the room, meaning none of the molecules can run around anymore. They have no more energy. Everything sits perfectly still at absolute 0. Then, as soon as you put any little bit of energy in, things start moving a little bit and a little bit. Now the temperature can go up from 0 on this absolute scale. So that's what Kelvin designed, a scale that really starts at the beginning of energy. It doesn't start kind of halfway in energy like Celsius or Fahrenheit do. So that's the story of the idea of Celsius, and Celsius, Kelvin, and Fahrenheit, and the measuring of temperature. Now, believe me, we're not done talking about temperature, because later we're going to talk about energy, and we will again tell more of the fable of temperature and how we use it to tell how much energy is in matter. And that will be weeks down the road from this point. Now, let me just conclude what we're doing here with these units. The amount of matter, how much stuff you have, is measured in what we call a mole. And a mole is kind of like the bushel basket of chemistry. You have to have at least a mole of matter to start talking about its quantity or how many you have in a pile. Now, a mole, it turns out, fits easily in the palm of your hand for most atomic materials. Like a mole of carbon easily will sit in the palm of your hand. So the idea of what a mole was to pile enough of it into your hand or into a test tube so you can see it. So the mole is designed to be enough that is visible to the naked eye, we'll say. Okay, so then we need some things that do light and electricity. So we have amperes to measure the flow of charge, and maybe we'll have more to say about it as well. And we have candela to measure the brightness of light. So we need units to measure something about how bright light is and how fast current is flowing in a wire. So these are the so-called SI units. And let me tell you, this is it. There's only 1, 2, 3, 4, 5, 6, 7 of these, but that's it. Everything is based, when we talk scientifically, it's all based on using these units. Nothing else is included. Now, when you look at that, that should make you go, how can that possibly be? How can I measure? My claim is I can measure everything using these 7 quantities. Anything I want to measure at all. Well, you should say, wait a minute. There's a lot of things I know of that aren't on this list. I see 7 things here, but where's the unit of speed? Where's the unit? I don't even see a unit of volume. I don't see volume. Where's voltage? I don't see any voltage on there. Where's the units of pressure? I don't see any pressure. How do I measure pressure? This is it. These are the units. How do I measure these other quantities? Well, what I do is I do what I call derived units. Anything else, again, let me go here. Anything other than these 7 is just combinations of these 7. So I can make anything I want from these. That's what I do. So let's look at maybe some familiar ones. Maybe this is one, and most of us said that we took 101. And if we took 101, I'm sure at some point you talked about velocity or speed. And I think your mom and them know what velocity or speed is as well. It's how you fly along, how far you have gone in a unit of time. And of course, your car measures this in miles per hour. The length is measured in miles. And then you record how many hours it took you to go that length. And you divide that time unit into the length of miles you went, and you get miles per hour. That's the speed that the car is going. Well, now what I'm claiming is if I'm doing it correctly as a scientist would, I don't use miles, I use meters. I'm supposed to use meters for length. I don't use hours, I use seconds. So the SI unit of time is derived from the formula for velocity. Since velocity is distance over time, I go to my list, I get a distance unit, I divide it by a time unit, and I get the SI unit that I'm supposed to use. Okay, now this is another little clue. I might give you a formula, and I'll show you all the things in the formula. Then I will say to you, from this formula, put it together, put the units together from the list that should be included to make the units of that formula. Okay, so again, the formula for velocity was distance over time. I would go to my list and I would find the distance unit of meters. I would find the time unit in seconds. And since the formula says divide the distance by the time, I would make the unit of speed as the meter unit divided by the second unit. So literally, whatever the formula is, which I would give you, you would just take the units for each of those values, put them together, and it will give you the units that you're supposed to use when you make the measurement. Now, a lot of times scientists give them other names, but like voltage is a combination of those units, but we call it volts, for instance. Okay, now, acceleration is the change in velocity with time. Now, above, and again, if you took 101, you probably talked about acceleration. Maybe you didn't speak very specifically about this idea of units, but here's what I would do. I know the unit of velocity from the line above. It's meter per second. To find acceleration, you see how the meter per second changes with time. So I have to divide the meter per second by seconds. And when I divide meter per second divided by second, you get meter slash second times second, or meter slash second squared. So the units of acceleration, meter per second squared. Now, the other thing you could probably do is just Google it, and it'll probably tell you what's the SI unit of this. It would tell you that, I'm sure. All right, now what about area? Area, of course, is length times width. That's the formula. If I know how long an object is, how wide the object is, I multiply the length times the width, and I get the area. Well, the units of length is a distance. The units of width is a distance. So to find the units of area, you take distance times distance. And that would be meter times meter. And of course, how we represent that is meter squared. So the square meter is the SI unit of area. Now, here's just another example. What about force? This is one of the most famous equations of all time. And again, I wouldn't expect you to know it. I would tell you this equation. It's mass times acceleration. So now what I do is I take the mass unit and I multiply it by the acceleration unit. And it's derived to be kilograms times acceleration units, or it's kg times m slash s squared, combination of all the units. Now what we do is we don't call it this. We call this a Newton. And this is very commonly done. We change the name to honor somebody who was a great contributor of the time. So many times, and probably if you were in 101, you talked about force, and you probably talked about force in units of newtons, but directly from the formula F equals ma, you could find the force in newtons. Now, just one more to show you an even crazier one. If you look at units of pressure, pressure is force divided by area. So all you do is you take the force unit and you divide it by the area unit. So I have the force unit that you see in kilogram meter per second squared. I have the area unit of meter squared. I divide the two together, and the SI unit of pressure is a kilogram divided by a meter divided by a second squared when you put them all together. And this is, again, given another name. In the metric world, we call that a Pascal, but technically it's this derived combination that you see on the right. Okay, so now what I'm showing here, and again, let's get this clear. I am not going to ask you a single question with regard to any of these. That is a promise, okay? Do we get that? You can't see my lips moving, but they are moving under my mask. And what I'm saying is that when we use this rational scaling of the units, we want to be able to move the basic units up and down to make them bigger or smaller so that the number can fit real nice, and the implication of how little or how big that number is hidden in the unit name. So we move the decimal not on the number, we really are moving the decimal implicitly in the unit when we use these so-called metric prefixes. Now, again, what I will say is we don't only use these for metric things, we use them for seconds. Seconds are not really metric because, as I talked about, there's this weird relationship between seconds and minutes and hours and days. Those are irrational. But what I'm supposed to use is maybe nanoseconds. And when you see the word nano, it instantly means 1 × 10⁻⁹, or 0.00000, or 8 zeros and a 1. So a nanosecond is just literally a billionth of a second. So I might use nanoseconds if I'm going really quickly. Nanoseconds of time are billionths of a second. 8 zeros and a 1, or 1 × 10⁻⁹ if you're talking scientific notation. I might talk in milliseconds. Milliseconds are thousandths of a second. Of course, that's a million times faster than a nanosecond. As crazy as that sounds, if you're going a million times faster than a nanosecond, you might want to measure in milliseconds. And if I go 1,000 times faster than that, I might measure just in seconds, because a millisecond is 1,000th of a second. Then there's kilo, mega. Mega, of course, means million, just like it does in computer stuff. I'm sure we're familiar with megabytes of storage, which is nothing nowadays. Gigabytes are billions of bytes. That's nothing these days. Terabytes is more like it, and the terabytes are 10 to the 12th, or that is trillions of bytes. That's where we are now. We're at the trillion level. And you know what? I cannot believe this. My bottom one is even actually wrong. I must have been not thinking correctly when I typed this. Notice I said exa. That's where, believe me, in the next 5 years, your devices that you're holding in your hand are going to be the next one up. Essentially, it's this. A megabyte is 1,000 kilobytes. A gigabyte is 1,000 megabytes. A terabyte, which is where we are now, is 1,000 gigabytes. What we're going to be in the next 5 years, without question, is the next one up. And that's going to be not exa that I have written there. It's going to be, that's peta, P-E-T-A. So I truly apologize. I don't know what the heck I was thinking here, That should be PETA at the bottom, and that's really 1,000 terabytes of storage. And believe me, I promise you, before you guys have kids, there's going to be terabytes of, I'm sorry, petabytes in your little handheld storage devices. When I was a kid, and when we went to the moon 50 years ago, the computers on the Apollo system had kilobytes of memory. I'm talking about kilobytes. Oh my God, that wouldn't even be one of your pictures you took, right? Your pictures are generally a megabyte each, generally. So you couldn't have stored one of your pictures, one of the pictures that you take on your phone, on the computer systems, which got us to the moon and back. When you stop to think about it, that's kind of crazy. It's kind of like, I will have to say, ingenuity has to take over in cases like that. We get a little lax because of the fact that we just throw a lot of memory at it. We just put it all, and you don't have to think cleverly about how to use it. In the old days, you really had to be much more clever because you just didn't have the kind of power that we have. Well, that's just part of the advancement of things, though. I mean, to think that 50 years ago, a kilobyte was where it was. A megabyte, it took a long time after that, probably 20 years after that, before the megabyte became available. But then only 10 years later, the gigabyte became what was standard. Then only 5 years later, the terabyte became the standard. So there's definitely been an acceleration in the level of technology. No question about that. None at all. Okay, so let me conclude my statement with regard to this slide. I already said it once, but for some of you that are phasing back in with me again, I am not going to ask you anything at all with regard to anything numeric or any connection at all between the usage of these prefixes. What I want to tell you, though, is you can attach these prefixes to any metric unit. You can scale length, time, mass, voltage, pressure, speed, anything you want using these mover uppers or mover downers, so that we can now rationally keep track of the values without, all we're doing is sliding the decimal point left or right when we apply these different prefixes. Much more sensible way of handling information than every time you want to do it. Well, you got to divide by 12 to change the feet. And you got to divide by 5,280 to change to miles. And that's just, it just doesn't make sense to do stuff like that. So, and one more time, I will mention that I don't know where I was. My head was not in the right place. The bottom one should not be exa. Exa is 1. Exa is 10 to the 21. So we're a little ways away from 10 to the 21. But 10 to the 15 is peta, P-E-T-A. So very soon they will be talking about petabytes of data on your computer, and it'll be 1,000 terabytes if you really want to think about what that would be. Okay, now here's the deal. We're going to stop there. Why? Because I blathered enough. We're tired of this. I posted lecture 2 on Wednesday. I'm going to start lecture 2. The remainder of things on here, I'm not going to quiz you on or ask you about. You can look at some of it if you want. I don't care. We're not going to talk about it anymore. We need to move on since we lost some time. So I posted lecture 2. We're going to do lecture 2 starting next time. I am going to put some things on Moodle to play with. And that's the story of the day. Peace out. Oh, how do you stop recording?